everyone. Welcome to our next Astro-Chat with Professor Don Kurtz. I'm Professor Andrei Zvelindovsky. I'm head of School of Mathematics and Physics in University of Lincoln in United Kingdom. I am joined here with our distinguished speaker and visiting professor, Professor Don Kurtz, who is physically now in South Africa. And although we are separated by distance and also by various restrictions and perturbances of virus, thanks to internet, we can come together in this virtual room and chat about astronomy and astrophysics. I know that there are many regular visitors in our Astro-Chat, but some of you might be here for the first time. So I just say a few words to introduce Don to the public, and then we will proceed with our Astro-Chat. Don is originally from United States, from California, from San Diego, where he obtained his education in astronomy in San Diego State University. And then he also obtained his doctorate degree, Doctor of Science, Doctor of Philosophy from University of Texas in Austin. He spent postdoctoral fellowships in Cape Town, South Africa. And then he spent almost a quarter of a century there, working his way up to a professor in astronomy and life fellow. After his time in South Africa, he spent another almost quarter of a century here in the United Kingdom, working in University of Central Lancashire till 2020. And now he is emeritus professor in University of Central Lancashire. And at the same time, we're very pleased that Don is also visiting professor in our school in Lincoln, University of Lincoln. And moreover, he is also extraordinary professor in Northwest University in South Africa, where he is physically right this moment. In his career, Don published over 500 of professional publications, authored a classical textbook, had more than 2,000 nights spent on telescope, and also served in the past as vice president of the Royal Astronomical Society here in the United Kingdom. I'm really very happy that Don spent every month, one evening, chatting with us about astrophysics. Now we move to our main program. Don will give presentation. After that, everyone can ask a live question to Don by putting question in the live chat of your YouTube channel. And with that, I give floor to Don. Welcome, Don, again to our Astro-Chat.
Thank you, Andrei. Good evening, everyone. Andrei has mentioned that I'm in South Africa, and of course we are approaching our summer solstice here. So as I sit here in my short sleeve shirt, 28 degrees and sunny today, this evening's still very warm. I think the conditions are quite different from what you're living with there. I was told 4 or 5 degrees in Lincoln tonight, and if you're coming in from elsewhere in the UK, you may even be colder. Now, let me share my screen with you for the presentation tonight. And check to make sure that this is working. Andrei, will you tell me whether you're seeing my presentation?
Yes, your presentation is visible.
Thank you very much. So what I'm planning to do, folks, for the next 3 lectures is a series of lectures about the death states of stars. Stars have lives. They're made of gas, but they're born out of gas between the stars, clusters of stars born at the same time, individual stars collapse, until they ignite hydrogen fusion and live most of their lives producing energy that way. 97% of all stars, our sun will one day too, die as what we call white dwarfs. In the next lecture, probably next month, COVID permitting, I'll talk to you about neutron stars, and the month after that about black holes. White dwarfs, the most common way that stars die, are absolutely fascinating objects. They were only discovered for the first time in the 1800s. This is a picture of the brightest star in the sky, Sirius. It's tremendously overexposed. Let me bring my laser pointer up here. There's the laser pointer. It's very overexposed because this picture is trying to show you its companion called Sirius B right here, where the arrow is pointing. These spikes you see on Sirius are not part of the star. Those come from diffraction in the telescope that took the picture. The light is just bent around the arms that hold up one of the mirrors, and so those are artifacts. The star doesn't have spikes on it. In 1862, an American telescope maker named Alvin Clark, in January of that year, was looking at Sirius with a superb new telescope he had just built, and was able for the first time to see this very faint companion, Sirius B. Sirius B has the same temperature as Sirius A. They're both 10,000 degrees. We know that Sirius B orbits Sirius A in just over 50 years. They're attached to each other. They're at the same distance. And yet Sirius B is more than, let me just see, 110,000 times fainter. I just had to calculate that, excuse me. And so it has to be very, very tiny. Here's an artist's impression, putting together two pictures of Sirius B next to the Earth. Sirius B, which has the mass of our sun, 330,000 times the mass of the Earth, is about the same size as the Earth. It is phenomenally dense. And most stars end up with first their cores and then their remnants, ending up in this state. A typical white dwarf has a mass of only about 60% the mass of the sun. Sirius B is a rather big one. The radius is typically bigger than the Earth. The more mass a white dwarf has, the smaller it is. Gravity squeezes it more tightly if it has more mass. Density of a typical white dwarf is about 1 million tons per cubic meter. Water here on the Earth has a density of 1 ton per cubic meter. You're mostly made out of water. And so these white dwarfs have a density 1 million times greater than you or me, 1 million times greater than seawater or lake water. With that tiny, tiny size and a mass approaching the mass of the sun, the gravity at the surface is about 350,000 times the gravity here on the Earth. If you could get in a spaceship and fly to near a white dwarf and hover above its surface, you would be squashed flat. Absolutely infinitesimally thin and flat. There's no surviving that for you or your spaceship. You don't want to get near a white dwarf. When they first appear in the sky, from the insides of the stars from where they form, they have temperatures around 200,000 absolute. This is very similar to 200,000 Celsius. And then they just cool with time, and the coldest white dwarfs we now know of are about 3,000 degrees absolute. The reason there aren't any colder white dwarfs than that is the universe is not yet old enough. Once a white dwarf forms, it simply radiates away its heat and cools with time. And with 13 billion years to work with, the coldest white dwarfs are now 3,000 degrees, and it is another way we measure the age of the universe. The maximum mass a white dwarf can have is 1.44 times the mass of our sun. A white dwarf cannot be any bigger than that, and we know that as the Chandrasekhar limit, named after the brilliant prodigy Subrahmanyan Chandrasekhar, who first calculated the size of a white dwarf. That's a story worth telling. Here are two pictures. One of Subrahmanyan Chandrasekhar at the age of 20, when he first came to the UK from then Madras, now Chennai in India. He came to do his postgraduate studies at Cambridge. At that time, the professor at Cambridge, the Plumian professor, and the world's most respected and highest powered astronomer, Sir Arthur Stanley Eddington, originally from Kendal in the Lake District, not too far north from the University of Central Lancashire, where Andrei and I first met when we were both on the staff there. So Eddington had the greatest authority of any astronomer in the entire world at that time. Chandrasekhar was a student, age 20, when he arrived in 1930. On the ship on the way to England, he calculated using general relativity, the new theory of gravity from Einstein, and statistical mechanics, quantum mechanics. He calculated the maximum size a white dwarf could have. Chandrasekhar and Eddington had quite a good personal relationship. They were friendly with each other. They talked frequently. They were both at Cambridge together. And personally, they got along rather well, but scientifically, it was a different story. By 1935, Chandrasekhar had completely polished his calculations, and he had done the final determination mathematically rigorously of what's now the Chandrasekhar limit. Eddington didn't believe it, and at a meeting in 1935 at the Royal Astronomical Society at Burlington House in London in Piccadilly, Chandrasekhar presented his work, and much to his surprise, he hadn't been told beforehand. Eddington then stood up afterwards and completely trashed it, made fun of it, laughed at it. And when the meeting was over, Chandrasekhar was leaving, people just said to him, well, too bad, too bad, too bad. And for decades after that, astronomers did not believe Chandrasekhar's work. They didn't believe his result. The physicists, the famous physicists of that time did. They understood it. They knew Chandrasekhar was right. But Eddington's authority was so strong that astronomers didn't actually believe this result about white dwarfs until the 1950s or even 1960s. Ultimately, Chandrasekhar got the 1983 Nobel Prize for that work. We do know who was right in the end. Eddington was a great astronomer, but he had some blind spots, and he was, well, as Chandrasekhar described him, he was obstinate. So the white dwarf can have a maximum size. For stars that are too big to form white dwarfs, they will form at the end of their lives neutron stars and black holes, and those will be the stories of the next two Astro-Chats coming in the coming months. Now, tonight we get some real astronomy here, even some real astrophysics. This diagram is one of the most important diagrams in all of astronomy. It is the most important diagram for anybody talking about stars. It was invented by two astronomers, Einar Hertzsprung, who's the H here in the HR diagram, and Henry Norris Russell, the most prominent American astronomer of that time. And what is plotted is a measure of the temperature of the star along the horizontal axis, ranging from about 2,000 degrees on the right up to over 30,000 degrees on the left. And then vertically is what plotted is how bright the star is. And in this plot, it's with respect to the sun. So our sun with a temperature of 6,000 degrees, and of course, one solar luminosity sits right here in the diagram. The stars can go up to very hot and very bright and very dim and very cool. This main band you see here is very important. That's known as the main sequence. And this is where stars in this plot spend almost their entire lives. This is where they are fusing the lightest element, hydrogen, to helium. And that's how stars live most of their lives. The hot ones up here are very massive. They can get up to a mass of more than 100 times the mass of the sun. Most stars are little tiny red dwarfs with a mass about 1/10, 2/10 the mass of the sun, and they reside down here. When stars get old, they swell up to be red giants and supergiants. We find them up here in the plot. The brightest of these supergiants up here are so big that if you put them where the sun is, all the planets all the way out to Jupiter would be inside the surface. And then when the red giants die, and I'll show you how they die, they do so spectacularly, they leave behind a white dwarf, and it just cools down this track with time. In the universe now, here are the coolest ones. Come back in 1 trillion years, and there'll be many, many much cooler ones farther down to the right. So that's the plot by which we astronomers think about and discuss the evolution of stars from their birth to their death. Here, in an artist's impression, is roughly what happens. A cloud of gas collapses in the galaxy between the stars. It forms an entire cluster of stars, but knots, seeds within the cloud, form into individual stars. And the typical star is even smaller than the sun. This picture is showing you one like the sun, calling it an average star. But some of the stars are much more massive. Those are those hot blue ones in the past diagram. They're down here. These average stars, in their lifetimes, eventually swell up to be red giants, and then they blow away their outer atmospheres into beautiful planetary nebulae, and the core down in the middle, left behind, is the white dwarf. 97% of all stars take this channel. The other 3%, when they're red supergiants, form iron cores, and they have what's called the iron catastrophe. And next month, I'll tell you about the iron catastrophe. They explode as supernovae, blasting matter back out into space with all the heavier elements, like the carbon, nitrogen, oxygen, that make up our metabolism and our biology, that came out of stars that exploded back when the galaxy was young. Their death state, neutron star and black hole. The stories for the next 2 months. Back to our white dwarfs for today. They come from first hydrogen fusion in stars. And so we're doing a bit of astrophysics tonight. I hope some of you are going to enjoy this. Hydrogen is the lightest, most common element in the universe. In 1925, an English PhD student, Cecilia Payne, was doing her PhD at Harvard College Observatory. She had been at Cambridge. She knew Eddington, but she couldn't do her PhD at Cambridge. In 1925, Cambridge did not award PhDs to women. So Cecilia went to America, where she did her PhD at Harvard, awarded by Radcliffe College. And some very illustrious astronomers have called her PhD thesis the most important PhD thesis ever written in astronomy. She showed that the sun is 90% made of the lightest element, hydrogen, 8% helium, and only 2% heavier material. Eddington, by the way, didn't believe her. Eddington was the one who first suggested hydrogen fusion as the power source for stars, but he didn't believe Cecilia Payne's result. And it was probably more than a decade later he finally conceded that she was right. What happens? These red dots indicate protons. That's what makes up hydrogen. Hydrogen's made of 1 proton and 1 electron. In the heat in a star, the electrons are pulled loose, and so 2 protons at temperatures of millions of degrees crash into each other, and they form what's called a deuterium nucleus. That's heavy hydrogen with 1 proton and 1 neutron. The other positive charge was spit out as a positron, an antiparticle, which annihilates with an electron, and a neutrino, which is a little tiny particle, hardly any mass at all, travels at nearly the speed of light, and everything in the universe is transparent to neutrinos, essentially. At the moment, as you sit listening to this talk, 10 to the 14, 100 trillion neutrinos are passing through your body every second, and they came out of this reaction in the sun a little over 8 minutes ago. They pass right through the sun, they pass right through the earth, they pass right through you. They're very hard to stop. That deuterium nucleus with 1 proton and 1 neutron now smashes into another proton, another hydrogen, and the 3 particles stick to make a light isotope of helium with 2 protons and 1 neutron. Another set of hydrogen atoms, protons, do the same thing. We end up with 2 helium nuclei. They crash into each other, spit out 2 hydrogen atoms, and end up as a nucleus of helium. And so the net result is 4 hydrogen atoms have fused to turn into 1 helium nucleus. And in the process, 0.7% of the energy of the mass has been turned to energy. And you all know that equation, even if you're not fully sure of what it means. Energy is equal to mass times the speed of light squared. That little bit of mass that disappears gets turned into energy. And that amount of energy is just phenomenal. This pathway was understood by the late 1930s. It was worked out by an immigrant to the United States, Hans Bethe, working at Cornell University. 12 years later, after Hans Bethe had worked out the pathways for hydrogen, we humans knew how it worked. Here's an example of an application. That is the most powerful hydrogen bomb explosion that there has ever been. And so shortly after discovering how the stars make their energy, we knew how to do it. We were making horrendous weapons. They're still in existence. But now we are trying to build power plants that will be powered by controlled hydrogen fusion. And this is an article from Nature, one of the most prestigious science magazines on planet Earth. And if you look in the lower left, this is just from a few weeks ago. And it's a major article about many companies that are getting funding to try to build controlled hydrogen fusion power plants on a small scale. And we're doing that on a gigantic scale down in Cadarache, France, at a cost of 10 billion euros. But this is on a smaller scale. They're now hoping to have hydrogen fusion power plants in 10 years. maybe 10 or 20 years, this is going to be a major energy source for humans later this century, the power of the stars. Now, as the sun fuses its hydrogen to helium, here's an artist's impression of what the sun will look like someday when it swells to be a red giant. The hydrogen turns to helium. The helium is denser. It settles to the core of the sun, making a dense ball of helium down in the core of the sun. This is the proto-white dwarf. As the helium settles, it releases gravitational energy. That makes the hydrogen fuse faster, and the extra energy is causing the sun to swell. It's getting bigger and it's getting brighter. And some of you just had the thought, oh, well, if that's the case, if the sun's getting brighter, maybe that's the source of global warming. And that's a serious question. We've looked at it seriously, and it is not the source of global warming over the last 2 centuries. The global warming that we're undergoing, the climate change, is us pumping carbon dioxide into the atmosphere, hydrocarbons. But the sun is getting brighter, and on a timescale of billions of years, it will evaporate the oceans, blow away the atmosphere, and essentially make the Earth unlivable. When the sun gets to be a red giant, as other stars already have, it will get so hot in the core, it will then begin to fuse helium to carbon. Now, here's the new fusion reaction inside the star. 2 helium nuclei made from the hydrogen fusion crash into each other, and they form a beryllium-8 nucleus. Now, beryllium is a very light metal, and it's incredibly strong and incredibly light. And for those of you who are paying attention, the James Webb Space Telescope, the great new space telescope we've been waiting decades for, is now due to be launched on the 22nd of December. The main mirror, the big mirror of the James Webb Space Telescope, is made out of this lightest metal that you can form mirrors out of, beryllium. This beryllium-8 is not stable, but in the 10 to the minus 16 seconds that it survives, it occasionally crashes into another helium atom, and then the 3 of them form carbon. There's the source of carbon in the universe. There's the source of carbon that makes up your chemistry, my chemistry, all of biochemistry that makes life possible in the universe. The carbon has been cooked up in helium fusion reactions inside red giants. And again, a little bit of mass disappears, and that then powers the red giant. In the case of our sun, it can power itself by hydrogen fusion for 10 billion years. It'll power itself by helium fusion for another 100 million, and then it will die in some massive pulsations that will blow away its outer atmosphere. Here's the great ring nebula and the constellation Lyra. The star has had some late thermal pulses and blown away its atmosphere and a lot of mass, and that little dot right there in the middle is the helium core, which is so dense it is a proto-white dwarf. These are some other examples of the way other stars have blown away their atmospheres quite spectacularly to leave behind the white dwarf core. That white dwarf core is predominantly made out of carbon, a little bit of oxygen mixed in with it, but predominantly carbon and oxygen for most white dwarfs. Now, you will remember from childhood this little poem, Twinkle, Twinkle, Little Star, How I Wonder What You Are, up above the world so high, like a diamond in the sky. Most people don't know that was actually written by somebody. 2 sisters, Anne and Jane Taylor, wrote that in London in 1806. They called the poem The Star. There are diamonds in the sky. This is a picture of a globular cluster taken from the ground. Here's a Hubble Space Telescope picture of just a tiny patch of that old globular cluster. And these rings are around the old white dwarfs in that globular cluster. Those oldest white dwarfs have now cooled to the point that their carbon cores have solidified. They have turned into one giant carbon crystal about the size of the Earth. De Beers can eat its heart out. Nobody's ever going to get near one of these and mine the diamonds, but there really are diamonds up there in the sky, the size of planet Earth, but with nearly the mass of the sun. In astroseismology, my own specialty, we proved that some decades ago with this particularly white dwarf. We call it Bruce. Its actual name isn't very romantic. It's Bruce Proper Motion Survey number 37093. But we can tell from the vibrations on the surface, it really is crystallized. Some of these white dwarfs turn into giant carbon crystals when they get old. Put into the audible, this is what the vibrations inside of that star sound like. Now, in 1925, this 25-year-old physicist one of the great physicists of the 20th century, Wolfgang Pauli, elucidated his Pauli exclusion principle from quantum mechanics. No two electrons can have the same quantum state is the rule. That is the cause of the elements of the periodic table. It's why we have elements and hence chemistry. And it's also the cause of the pressure that supports a white dwarf against collapse. The sun has got a lot of gravity, but inside the sun, the hydrogen fusion's producing energy and the gas pressure pushes out and balances against gravity. But when the sun dies and there's no more fusion reactions down in the core, it will squeeze until the electrons are now squeezed to the maximum density that the universe allows. The Pauli exclusion principle says you cannot pack electrons more tightly than what this rule says. And it's that pressure from the electrons, the inability for them to be squeezed tighter because of this rule, that pressure is what balances gravity and keeps a white dwarf from collapsing any further. White dwarfs are really common. 97% of all stars end up as white dwarfs when they die. Now, the maximum mass a white dwarf can have is 1.44 times the mass of the sun, but stars up to 8 times the mass of the sun still end up as white dwarfs because they blow away their outer atmospheres in winds, and then they throw off their outer atmosphere in planetary nebulae, or they're in binary stars and they pour a lot of their material onto their companion star, leaving behind only the white dwarf. White dwarfs are often in binary stars, 2 stars orbiting each other. And when the white dwarf forms, if the other star is then swelling to be a red giant, we end up with something called a cataclysmic variable. And the star that's like the sun, swelling to be a red giant, then dumps material towards the white dwarf. And because they're orbiting each other, that material ends up in a disk around the white dwarf, spiraling in onto the surface of the white dwarf. This material is mostly hydrogen. That's what stars are made out of. And when enough builds up on the surface of the white dwarf explodes as a giant hydrogen bomb. It goes off as what we call a nova. And it can get 10,000, 100,000 times brighter briefly for a few days. It can do that repeatedly on a time scale of decades and centuries. Tiny bits of stuff piling up on the white dwarf can even produce dwarf novae, which will in fact have little tiny explosions many times per year. If a white dwarf happens to be near the Chandrasekhar mass, or maximum mass a white dwarf can have, and it's orbiting about a companion star, dumping material onto it, when the material dumped onto it leads it to reach the Chandrasekhar mass, almost, the temperature of that carbon and oxygen in the core reaches billions of degrees. And now, instead of the hydrogen on the surface going off as a hydrogen bomb, the entire star explodes by carbon fusion as a carbon nuclear bomb, and the star blows up. It blows itself to bits as a supernova. This is a special type of supernova. It can get up to 5 billion times brighter than the sun, but every single star that blows up this way has exactly the same mass when it blows up. And so it reaches the same absolute brightness. And we now know how bright that is from calibrating that on nearby supernovae that exploded in nearby galaxies we know the distance to. And so these are the brightest things we can see far out into the universe. And when you're told the expansion rate of the universe, when you're told that we now say the universe is accelerating due to something called dark energy, that measure of the expansion of the universe, that measure of the acceleration comes from these standard candles, these supernovae, which are exploding white dwarfs. White dwarfs are really very important. Now, they can do some very exotic things. Sometimes you get 2 white dwarfs orbiting each other. Here's an artist's impression of 2 such stars. The bigger one is the lower mass one. The bigger the mass of a white dwarf, the smaller it squeezes, until when it reaches the Chandrasekhar limit, it collapses to either a neutron star or a black hole if it doesn't explode. We'll talk about that in the coming months. There's a telescope in California called the Zwicky Transient Facility. It's looking at every variable thing in the northern sky every night that it can observe. The star names are no longer so romantic as the old Arabic names for stars. We just have billions of them, and so they have names that are based on their positions. But this Zwicky Transient Facility found 2 white dwarfs recently orbiting about each other in 6.91 minutes. Those two stars have orbited each other more than twice since I started talking to you. And if you could bring the two of them here to the solar system, they would fit inside Saturn. They are so tiny. They're Earth-sized. The Zwicky Transient Facility also just last year discovered one white dwarf that rotates in just under 7 minutes. And it has a radius. It's almost at the Chandrasekhar limit. It's about the size of the Earth's moon, phenomenally small. It probably is the result of two white dwarfs crashing into each other. And so now I'm going to show you a little movie. This is put together by astronomers working on these orbiting white dwarfs. They are potential sources of what's called gravitational radiation. As they orbit each other, due to Einstein's general relativity, we know that they are radiating gravitational waves. They lose energy, and that makes them come closer and closer together, so they orbit faster and faster and faster. Until finally, when they get close enough, they will merge with each other and put out a pulse of gravitational waves, ripples in space-time itself, which travel out through the universe. And those can now be detected by gravitational wave observatories here on the ground. So far, they're detecting crashing black holes, much more massive, crashing neutron stars, but soon we'll be detecting crashing white dwarfs too. And again, sometime next year in one of the Astro-Chats, I will talk to you about the gravitational waves. So white dwarfs are forever. They just radiate over the leftover heat from the star they form from. Sometimes they can put out so many neutrinos that they're actually shining brighter than these neutrinos that penetrate everything than they do in light. But as they cool, they'll eventually become something we call black dwarfs. Black dwarfs haven't happened yet, but that will happen someday in the far future when no more light comes from them. They're made out of elements. The nuclei inside them, carbon and oxygen, have got protons and neutrons. We know the neutron's not stable. The proton, if it's stable, black dwarfs will live forever, for an infinite time into the future. If the proton's not stable, and some theories suggest it won't be, then someday white dwarfs will evaporate. But by someday, we already know the proton has a lifetime greater than 10 to the 34 years. That's 10 to the 24. Let me just do this. 100,000, million, billion, trillion, quadrillion, quintillion, sextillion, septillion. If you don't like these numbers, that's a septillion times longer than the current age of the universe. Minimum age for white dwarfs to live to. White dwarfs really are forever. When they cool, they turn into diamonds. So De Beers didn't get that completely wrong. These diamonds really are forever. It's time to take questions now, folks. Thanks for your attention.
Thank you very much, Don, for this fascinating presentation. And now we, as always, open for questions. The questions you can type in a live chat in YouTube, and already I've seen there are some questions arrived.
Andrei, are you seeing me now rather than my presentation?
Yes, yes, yes.
Thank you.
I see you. And just before I read questions, maybe I ask myself. Then I was in University of Central Lancashire at the same time as you. I took my friends from Canada who were interested in Einstein theory. They work in that, and to Kendall, in fact. To the Kendall Museum, and we tried to ask museum attendants about Eddington. They did not know quite well, but we found there was indeed some exhibit there. And there is an astronomical society even in Kendall named after Arthur Eddington. Is it right?
I've spoken to them several times, Andrei.
Right. It is really kind of fascinating that basically in the center of Lake District there is this quite beautiful kind of a place with this attraction to astrophysics and history. So
Eddington is Kendall's greatest person ever.
And it's also amazing that how strong his influence was. In not just kind of related to Einstein, but also here, and it's had kind of a very interesting effects which you mentioned, which some of them I did not know. Thank you.
A very powerful intellect and a very powerful position.
Right. Okay. So now we go into questions from the public, and there is question from John Leventhal. Why there is a limit to white dwarf size?
Right. That was John, did you say?
Yes,
Or
John
John.
Leventhal. Yes.
John, the answer to that, let's see if I can help with that. This is what Chandrasekhar actually discovered and proved. When you pack the electrons, there's no way to make this totally simple. You can pack 2 electrons at a certain speed into a tiny little volume of the star. If you have electrons traveling more quickly than that, they can be packed into the same volume. And then if you have electrons traveling even more quickly, they can be packed into the same volume. And so with more and more faster and faster moving electrons, you can pack them to higher and higher and higher density. And with the stronger gravity, the white dwarf gets smaller and smaller and smaller as they get packed more tightly. But there's a limit to how fast electrons can travel. And that's the speed of light. And that was what Chandrasekhar handled that hadn't been done before. He used special relativity and calculated that when finally the electrons get going to near the speed of light, you end up in a situation where the gas behaves in a different way and the pressure no longer depends on the density. And all of a sudden, the radius just collapses to 0. Within the theory, it actually does go to 0. And you think, how can anything go to 0? That would be infinite density. That's the talk in 2 months' time about black holes. We'll come back to that. But that is the reason there's a limit, is you get to where the electrons are traveling even at the speed, almost the speed of light, and they're packed as tightly as they can be packed. And the gas now no longer behaves in a way that provides pressure to resist the gravity. It changes its character, something we astronomers or physicists call an equation of state for the gas. Actually, let me just go beyond that. Some of you will have done chemistry at school, and you will remember an equation called PV equals nRT, the perfect gas law. Well, that gas inside the white dwarf is no longer a perfect gas. It behaves very differently. I'm sorry that couldn't be made easier. It's a calculation that our undergraduates can do at 3rd year level at university now.
Thank you. Now there is a question from AC. Is Sirius B the closest white dwarf to the Earth?
Is this AC from San Diego?
I don't know. AC, are you from San Diego?
He or she can tell us. I think we may have had questions from AC before. The answer is yes.
Yes, so San Diego indeed, very early, yes.
Okay. Well, hello to San Diego, AC. The answer is yes. I'm not absolutely sure, AC. Sirius is only 10 light years away. Is there a white dwarf closer than that? Let's keep going with these questions. And I'm going to do what we all do and see if somebody else has got a definitive answer for that. All right, the internet, whoever's doing Wikipedia, which we can trust so-so, thinks that Sirius B is the closest white dwarf. And so my guess is right. The white dwarfs are faint, but we can see them when they're that close. Now, if you ask me where the closest black hole is, I'd have to tell you, well, they're invisible. I don't know. And if there's one close and it's coming closer, we may be in trouble. We'll come back to that. But the white dwarfs, yeah, Sirius is the closest one.
Thank you. Thank you. And then I see there was discussion here between a few people, and I just read it, and you maybe can comment on the member of audience named Shay says that after white dwarf passes the limit, it collapses because its core can't support the pressure anymore.
Okay, the core can't fight against the gravity. Normally for a star, pressure pushes out, gravity pulls in, and they're in what we call hydrostatic equilibrium. In the case of the white dwarf, when the mass isn't too great, the pressure from the electrons, we call it electron pressure, can push out and withstand the gravity. But when the star gets to the Chandrasekhar limit, the pressure pushing out cannot withstand the gravity pushing in. The gravity is too great. Now, just to give you a preview of what's coming, the electrons cannot be packed more tightly, but they also can't resist the gravity, and the thing gets smaller. So what happens? Is a law of the universe broken? And the answer is no. All of the protons are pushed into electrons, and they're all turned to neutrons, and there aren't any protons left anymore. There aren't any electrons left anymore. And now you're not breaking the Pauli exclusion principle for electrons because the electrons are gone. Aha, but the neutrons have a Pauli exclusion principle too. And that's next month's story.
All right, thank you. And it just this question was discussed with Tom James, who asked Shay, yes, but why? And Shay actually put a bit of answer, something about electron degeneracy of pressure. So that limit is like the maximum amount of mass the core can support before it goes boom. So I think you kind of answer Don reasonably clear to that.
Now, Andrei, you just brought up a word, and let me now say to the other people who are listening, we call this gas, when the electrons are packed to the limit the Pauli exclusion principle allows, a degenerate gas. And it does not behave the same way that a normal gas behaves. With a normal gas, if you heat it, it expands. We use that all the time. Go fly a hot air balloon. Heat the gas, it expands, and you can now fly your hot air balloon. But with a degenerate gas, when you heat it, it does not expand. And so it doesn't behave in the same way. And it's part of the reason we say that it's in a degenerate state.
Thank you. Thank you. Then I see there is a question from Team Play. Why white dwarfs sometimes turn into black dwarfs?
Oh, okay, Tim. The white dwarfs haven't yet turned into black dwarfs, but all white dwarfs ultimately will turn into black dwarfs. So you've got a good question. The white dwarf is the remnant of the core of a star that shone throughout its entire lifetime, produced tremendous heat from fusion reactions. And so when the white dwarf forms, the electrons don't have a temperature, they're degenerate. But the nuclei, the carbon and the oxygen, are not degenerate, they have a temperature, they're hot. And anything that's hot radiates light. And so the white dwarf shines. You saw the picture at the beginning of the Sirius B, it was shining light. The white dwarf is shining away the energy left over from when it was the star that made its own energy. But it doesn't have any new source of energy. And so with time, it will grow dimmer. And a good analogy, imagine that you have heated something in a fire. Let's say you're out at a campfire. And you may have heated a stick and it's glowing red. You pull it out of the fire and leave it sit there and watch it. What does it do? It cools and it fades. And that's exactly what the white dwarf is doing. It no longer has a new source of energy. It's simply radiating away the leftover energy. It's very well insulated, so it takes a long time to do this. But over 13 billion years of the universe, 12 billion years since the first white dwarfs were formed, they've managed to radiate away enough energy they've cooled to 3,000 degrees. Come back in billions of years, they will have cooled to 2,000, but they'll still shine in the red. Come back in hundreds of billions of years, and they will have cooled to where they're only shining with a little bit of low energy radio waves. And ultimately in the future, they will cool to the point they don't radiate anymore at all and become true black dwarfs. So there isn't any black dwarf yet, but it's very clearly, obviously, the fate of the white dwarf to become a black dwarf someday.
Thank you. And then there is a question related from Scarpo, who puts his name, Jacob. How exactly do black dwarf evaporate?
Well, Jacob, the black dwarfs don't exist yet. So is your question perhaps how do white dwarfs operate? And the white dwarfs, I'm now just reiterating a little bit of what I said, but they are basically just there. They have plenty of mass, they have gravity, they have a little bit of leftover heat. But unlike young stars, they don't have any way to generate new energy. And they don't have any way to blow strong winds off their surface. Now, if they're in a binary star and stuff's being dumped on them, then you get some pyrotechnics, because as the stuff piles up, it can be ignited in hydrogen fusion. You get novae and dwarf novae. But otherwise, the white dwarf just sits there, either orbiting the other star it's orbiting, or if it's out there by itself, just coasting along through space. Not a very exciting life once a star becomes a white dwarf.
Thank you. And then John Leventhal asks again, do white dwarfs have any structure, or are they homogeneous?
Oh, thank you. Thank you very much, John. No, they have wonderful structure. That's an incredibly good question. Only the very core of the white dwarf is degenerate. And that is made of typically carbon and oxygen, and it is uniform. It's of uniform density, it's of uniform temperature. But sitting on top of that is a very thin gas, which is not degenerate. And that's typically, for many white dwarfs, a little bit of leftover hydrogen. For some of them, the hydrogen's gone and it's leftover helium. And for a very few, even the helium's gone and it's carbon. And if it's got hydrogen and helium in the atmosphere, that stratifies with a helium layer underneath and the hydrogen on top, because hydrogen is lighter. And with my own specialty, and in stars I've even worked on, we watch the vibrations in those stars. And from the way they vibrate, we can actually measure the thickness of the hydrogen layer and the thickness of the helium layer before sitting on top of this degenerate, uniform density, uniform temperature core. Very good question. They are stratified, they have structure, and we can actually see the structure.
Thank you, thank you. I see now arrived a message from Phil Morris, who writes, on behalf of Eddington Astronomical Society of Kendall, many thanks for your kind words and your past talks to us.
It's a pleasure, Phil. And although tonight I was highlighting Eddington's dispute with Chandrasekhar, which Eddington lost, Eddington, there was a reason why he was the most illustrious astronomer in the world at that time. American astronomers were actually surveyed in the 1930s and asked if they were to list who the most famous astrophysicist on the planet was, who would they choose? And every single astronomer question put Eddington at the top, and some of them even said, and the next person down is 30 places below. He was phenomenal. Even if he wasn't right about Chandrasekhar and he wasn't right about Cecilia Payne. You know, it was his book, The Internal Constitution of the Stars, which I read as an undergraduate too. Chandrasekhar got that book when he was in high school, and that was his motivation to go to Cambridge and to do theoretical astrophysics.
Right. Thank you, Don. There is here also a comment from Minerva Bird, who writes, neat. It is like a new music of the spheres, except the vibrations with white dwarfs and not planetary orbits like Kepler posited.
Minerva, that is, I think that's exactly right. The vibrations in the stars are the new music of the spheres. Kepler posited that music of the spheres was related to the orbits of the planets, but let me just tell you where Kepler got that. Kepler believed in the music of the spheres of Pythagoras and the Pythagoreans. So now we're talking 600 years BC. Kepler was wanting the planets to be in harmonic series because of the music of the spheres of his predecessor, Pythagoras, 2,000 years before. And the Pythagoreans believed that each of the planets, the sun and the moon and the stars, moved on crystalline spheres that spun. And as they spun, they hummed and made a music of the spheres. And the gods could hear the music of the spheres. And someone with superhuman intellect, like Pythagoras himself, could hear the music of the spheres. I now know that I've reached an old age that Pythagoras had tinnitus, rather than was hearing the music of the spheres. So the music of the spheres came from the spinning of these crystalline spheres as a model of the universe, to Kepler, who wanted the orbits of the planets to fit into this harmonic series. and after more than a decade of trying to make that work, realized it didn't work, gave up his cherished idea and went and found the correct Kepler's laws. And then now we have finally discovered that there really is a music in the stars. They ring like giant bells.
Thank you, Don. Thank you. And Minerva Bird replies, it always goes back to the ancient Greeks.
A lot does. It goes beyond the ancient Greeks. The astronomy goes back to the Babylonians, the Sumerians, the Arabs, even further back.
Thank you. There is a question from Sean Childs. Is our knowledge of white dwarfs good enough to negate them from observations from newer telescopes so we can focus more on what we can see?
Oh, that's an interesting question, Sean. The white dwarfs themselves are absolutely fascinating for some very, very high energy physics. And so we actually want to use the bigger telescopes that are being built to observe the white dwarfs even better. I barely mentioned that some white dwarfs shine most of their energy out in neutrinos. And neutrinos, we catch a few neutrinos with our neutrino experiments, and that has led us to discover that neutrinos have got a mass. That's changed our view of particle physics. There have been a couple Nobel Prizes out of that. But we have got some hypothesized particles to try to explain this dark matter. One hypothesized particle is something called an axion. And if axions exist, they will affect the way white dwarfs cool. And so if we continue to observe white dwarfs in even more detail with the vibrations in them, we can measure the cooling rate. And the cooling rate may measure whether there are axions in them and actually then directly tell us something about the standard model of particle physics. And so I'm sorry, to the contrary, we want to look at the white dwarfs in much more detail. And we want to use the giant big telescopes being built to see those white dwarfs much more clearly.
Thank you.
I am, as you can hear, a white dwarf fan.
Thank you, Don. There is a question from David Talbot here about fusion. David writes that fusion have been for 20, 30 years away since I was in a school in 1970s. So presumably question 20, 30 years past.
Yeah, I think you, David, is it?
Yes.
Yeah, David, I think what you're asking about is this promise of controlled fusion. And you're right that when you were in school, the word was that we would have controlled fusion power plants in about 40 years. When I was at university, which was before you were at school, we were going to have controlled hydrogen fusion in 40 years. We are now, I mean internationally, European Union, the UK, Canada, China, United States are funding the International Thermonuclear Experimental Reactor that's being built. It's under construction and it's very far along now in Cadarache, France. And that should produce a lot more power than is put in, but it's still experimental in terms of developing fusion power as a readily available energy source for humans all over the planet. And we expect that to be operational within a few decades. That article I showed you from Nature is a bunch of small companies that think they've got ways to get to this faster. And maybe we'll be producing energy on a time scale of 10 years. Let's presume, because they're also trying to attract investors, they're being optimistic. So maybe we're still thinking, oh God, could it be 30 years, just like when you were at school? But I want to make a point. Those of you who are looking, you can see Andrei there on the screen. And do you see behind him, what's behind him? Lincoln Cathedral. The people who built Lincoln Cathedral, when they laid the foundations, they knew that they would never see the end of it. It took well more than a century to build that cathedral, but they started it anyhow, and they knew it would be completed. Hydrogen fusion will happen. This is an engineering challenge. We understand the physics. And if it's 30 years from now, 50 years, 100 years, the time will pass. Look at that cathedral sitting. How old is that cathedral, Andrei? 1,200 years?
Yeah, it's from 11 centuries.
All right, 900 years, 1,000 years. The time will pass. The hydrogen fusion problem will be solved. It's not going to be solved in time for our problem of global warming and climate change. We've got to handle that much more quickly. And of course, along the way, we will have more and more renewables. But the hydrogen fusion will produce abundant energy with some radioactive waste. Our current fission power plants produce radioactive waste that will still kill you 1 million years from now. And we don't yet know what to do to store it for 1 million years. We don't have any societies that we think are stable on that time scale. The nuclear fusion will produce radioactivity that will be dangerous for maybe 100 years and then not a problem. And one can imagine keeping control of things on a time scale of a century. So we're not worried about the radioactivity from the fusion power plants like we are from the fission power plants.
Thank you. Thank you, Don. There is a question on details of white dwarfs vibrations from Jim K. How are vibrations of white dwarfs detected?
Yeah, Jim, the way we detect the vibrations in all stars, the main way is they cause the star to get brighter and dimmer. It vibrates in light. So as the waves run through the star gets hotter and cooler, and the amount of light that comes out depends on the temperature. And so it vibrates, getting hotter and cooler, and the light goes up and down. And what we do is we put our telescope on it, we just measure how bright it is, in some cases every 10 seconds, and just watch it vibrate. And then using mathematical tools, we can extract the frequencies of the vibration, and those frequencies depend on the structure of the star. Just like the structure of a musical instrument gives the timbre to a musical instrument, and it characterizes the notes coming out of that instrument, the structure of the star characterizes the notes. We can detect the notes from the light variations.
Thank you. I see one more question from AC. Is there any object left after type A supernova?
After type 1A supernova?
Oh, 1A.
Yes, AC, yes, there is. There's one of two types of objects left. And those were the other two things I didn't tell you about on that other pathway of stellar evolution, either a neutron star or a black hole. Possibly the entire star could be shattered and not leave any remnant. But mostly we think neutron star or black hole. And next month I'll tell you the neutron star story, and the month after that, the black hole story.
Thank you. And then there is a question from Kivispur. Can a white star support a solar system? Is it possible?
Can white dwarfs have solar systems? The answer is yes. And they may well still have planets about them. The sun one day will become a white dwarf. In the process of becoming a white dwarf, the sun will certainly swell up large enough to swallow Mercury and Venus, and it will then turn them to gas and evaporate them. It will certainly blow away the Earth's atmosphere and its oceans, melt the continents. It's uncertain about whether it will swallow the Earth and evaporate it. So the Earth's right on the edge. But Mars will survive, Jupiter, Saturn, Uranus, Neptune, Pluto, and the trans-Plutonian objects, they will all survive when the sun becomes a white dwarf. They will continue to orbit that white dwarf, but the white dwarf will provide a pitiful amount of light and they will become very cold. So yes, white dwarfs keep the solar systems they were born with, except for the close planets, because they eat the close planets when they become red giants.
Thank you. And maybe last question from Scarpo. Are all electrons in a white dwarf degenerate?
Oh, the answer is in the core, yes. In the atmosphere, no. So throughout most of the white dwarf, almost the entire mass, they're degenerate. But there is a thin layer, about 1/10,000th of the entire mass, floating as a layer of hydrogen on top of another thin layer of helium, but constituting only perhaps a 10,000th of the whole mass of the star. And so if you would like to neglect the 10,000th, then all the other electrons are degenerate.
Thank you. Thank you, Don. And we exactly on time. We exhausted our time today. Thank you, Don, very much for answering questions. Thank you, everyone who came to this Astro-Chat and asked questions, participated in discussion. It was a pleasure to be with you in this virtual chat room, and we hope to have a next one in about 1 month's time. And we both wish you seasonal greetings and best time for the coming new year.
Andrei, may I just jump in
Yes.
here? To the audience, I would like to tell you that Andrei and I suggested I would like to do the next talk on the 7th of January. And Andrei said, oh, but you can't. I will be home with my family, and that's Christmas. And for him, it is. And have I done that talk in Astro-Chat, Andrei, about why that's Russian Christmas, the calendar? No, someday. I've done it live at Lincoln, but I haven't done it as an Astro-Chat. So we can't do it on the 7th of January because that is Russian Orthodox Christmas, and Andrei will be having Christmas dinner with his family that day. We'll find a date in January sometime.
Yes. And indeed, it's good to have chat also about these differences in calendar.
Yes. Sometime next year, maybe.
Yes. Thank you. Thank you very much, everyone. And thank you very much, Don. And I hope to see all of you again in our virtual chat room. And one day I will hope to see some of you next to this cathedral. Okay. Bye.
Bye, everybody.